Hello and welcome everyone to another webinar series from ADS, from the A to Z in data science series. Today we're partnering with the Study Association from the VU called SABA, and we're here to bring you a webinar on computer vision. To quickly introduce myself and ADS, I'm Anita Awalaja and I work with Amsterdam Data Science. And in short, Amsterdam Data Science is a network organization that seeks to promote the data science and AI ecosystem here in Amsterdam. And we do that by connecting industry, society, and academia. And one of the events we do are events such as these webinar events to give people, more knowledge within the field of AI and data science. I'll now let Serhat from SABA introduce his study association.
Thank you. Yeah, so SABA stands for Study Association Business Analytics. We are an association at the VU. We're also quite young. This year we're entering our 4th year of existence, so pretty exciting stuff. Our students, well, our curriculum consists mainly of mathematics and programming, and with that it's just mathematical optimization, and the programming part is more data science, machine learning, and yeah, so our interests are mainly in data science. And we're also, since we're young, we're still looking for interesting collaborations with interesting companies. So if you would like to collaborate with future data scientists, feel free to contact us. The email is in the slide. Otherwise, you could go to our website, saba.amsterdam, and then you can find some contact link somewhere.
So today we are joined by Benedikt and Inske and Stevan as well. And I'll let Stevan introduce himself.
It's already afternoon. My name is Stevan indeed, and I'm an associate professor of artificial intelligence for business. I'm working at the business school of the University of Amsterdam, and my research focuses on multimedia analytics, so analyzing large quantities of images, videos, information about users, and applying those techniques to solve different problems in the domain of urban computing, basically improving livability of our neighborhoods, business, such as, for example, marketing, and some security applications, basically analyzing different online communities that could be potentially harmful for the society. So that's in short about me. Thank you, Anita.
Perfect. See, perfect. So yes, I would like to end the poll now and share those with you. So before we start, I would like to introduce both speakers, starting with Benedikt Fuchs. Sorry, Benedikt, I'm pretty sure I've pronounced your surname incorrectly. My apologies. I think it's Benedikt Fuchs. So Benedikt studied visual computing at TU in Vienna. He's been working as a data science at Cloudfight for the past 3 years. He's designed various NLP solutions for real-world applications and keeps a radar on various emerging technologies. His presentation today is called Adversarial Attacks and Autonomous Cause. While adversarial attacks have not found any real-life uses so far, it has enormous potential to be harmful. One of these potential dangers is the deception of autonomous cause. Benedikt will explain how these attacks work and what the consequences of these attacks are. So without further ado, I'd like to give Benedikt the floor.
Yeah, thank you, Anita. So yeah, I'm Benedikt Fuchs. I work at Cloudfight, and before I begin with my talk, I would like to talk a little bit about Cloudfight. We are a software and AI company with about 400 employees, and we have a very broad range of projects for various customers. We just recently had the Cloudfight coding contest. I hope you heard about it before, and you can now see on the screen. It's a big event which is held usually twice a year, with a lot of people participating, and I hope the next time you will participate too. And I really recommend checking us out. We just recently moved in Amsterdam to a bigger and newer office in the city center. So please check us out. So my talk today will be about adversarial attacks, or how I also like to call it, cybersecurity in AI. Because I think it's also important to have some understanding of what cybersecurity is when you talk about it. Because when we talk about hacking, it has different meanings. So a colleague of mine some years ago told me that he was scared because he read in the news that his ATM machine around of his bank were hacked, and he was scared about his money being not safe anymore. So what you need to understand is there are 3 types of hacks which have different aims. The first hack is when you basically shut down the ATM for a moment. That's called a hack on the availability. Another hack would be if you manage to leak information. That would be a hack towards the confidentiality. And the third range is if you manage to alter the behavior of the ATM. For example, if you install Doom on it, or make it inject all the money on the insides. And that's called a hack on the integrity. And obviously those 3 types have a different level of impact. So in the case of my colleague, hacking the ATM meant that the ATM was down for a certain amount of time. So obviously that's bad, but it still means the money is completely safe and he doesn't need to care about that. With that, let's go to adversarial attacks. This is one of the default examples. We see here 2 images of a panda, and I guess no one here can really see the difference. Probably some can tell it because it's a famous example. The difference is on the left side, a neural network would say, this is a panda, and it would be quite sure that it's a panda. And then on the other side, it would say that's a given, and it's even more sure. Mathematically speaking, the difference can be explained like this. There is this smallest unit possible, which is basically the least significant bit, and there is this mask that is added to it, which alternates the prediction of the neural network. In terms of cybersecurity, it's really important to notice this is an attack on the integrity, because you basically alternate the behavior, what will be done with the prediction. So to explain how this works, you need to know what I mean when I say AI in this context. I'm mainly talking about neural networks, but also about other machine learning models. And they usually work in the way that you have an input, and for this input you create some and generate some predictions over a function. And this is usually learned via a forward pass and a backward pass. So you first make a prediction, and then look at the expectation and alter some variables based on the difference of the prediction and expectation. So in an adversarial attack, you would change the expectation that you then say, we don't want to have a panda, but we want to have a gibbon. That's one important step. And the other is that you don't change the neural network, the so-called gradient of the parameters, but you rather change the input, which is something that you can do with each neural network just by the way that they are built. So the main reason why adversarial attacks work so good is because AI doesn't actually learn a task. It learns the data that it gets, and small variation can therefore also vary in the results. So yeah, so again, this mask that we see here is not something something that is randomly chosen, but that's really something that's learned. So in the case of real life scenarios, we can quickly see that just changing the input image is not really helpful, because almost all systems have the camera integrated in it, so you cannot just change an image. So this adversarial attack that I just have shown is kind of limited. However, researchers have shown that this limitation is not too hard, because they managed to 3D print a turtle. This turtle is quite robust and will be classified as river, which is also not really a use case that is interesting, but it shows already that there is potential to also alter the 3D three-dimensional world. So let's go to the autonomous cars. There's one attack that I find quite interesting, which is called the sticker attack. So this is a stop sign, but just because there are those stickers put on it, it will be it will have a different prediction, and this can be used to purposely create accidents. Like if the car doesn't see the stop sign, maybe then also doesn't see a passenger, then it might have a huge impact. And the scientists really tested it in real life scenarios. They call it drive-by testing, and they managed to fool the predictions out of several times. So how does that work? The idea is basically the same as it was with the panda example, just that they don't just optimize one image, but they create a lot of physical and transformations of the same image, and then optimize the pixel over the average of those images. So and they use a mask which they then set to only modify certain pixels. Those pixels what then will be used on the stickers. With that, they create quite good results. And other scientists thought that's kind of boring, that's not really useful, because stickers are obvious. Like if there's a sticker on a road sign, you see it, and you can rather quickly say, okay, there was an attack, and see if you want to prohibit somehow. So they claim that they managed to do the same with laser pointers. Sadly, their publication is not freely accessible, so I didn't read it and didn't verify it, but it sounds a bit terrifying to me. I did, however, what we have to say is that all those attacks that I showed are so-called white box tests, where the attacker basically had access to the whole neural network and therefore could access could easily see how to modify it. There are also black box attacks, which are way harder because there you don't have all the information. So basically, on a white box attack, you can access everything that the neural network has, and then but you could restrict it. For example, you say you only output the confidence scores, and then it's not possible anymore to calculate the gradient, but it's still possible to approximate it with more effort. And same is also if you don't have the confidences, but only the output labels, it gets way harder to do such an attack, but it's frequently shown that it's still possible to do it to some extent. So what I want to give you from what I learned is adversarial attacks are still in the processing. There are a lot of attacks, but there are also a lot of defenses. And right now it's an arms race. Like sometimes there comes a new defense, which shows that certain attacks can be avoided. And then later there might be a new attack that manages to also break that defense. The thing is right now, as long as it's not really determined, I think it's important to keep in mind that it's quite likely that your defense will break sooner or later. Second is that there is a theoretical potential for quite deadly crimes. Therefore, I think it's quite important to take those into consideration. However, as far as you know, there are no real-life issues with it, which I think is a quite positive message. So we are still at the case where we can ensure that also no issue and that adversarial attacks won't be an issue in the future too. And that's it. Thank you for your attention.
Thank you very much. This was really great, Stevan here, by the way. For those that joined a little bit later, I am going to be moderating the session. And just to remind you that you can pose the questions to Q&A box. And we can use chat for example, some casual questions, but the questions to the speakers should go to the Q&A box. And while you're finding your way around Zoom, actually, and it's a bit of lunchtime probably, so it takes a little bit of warming up. So I'll first thank Benedikt for a really great presentation, and this really points a very important issue and really kind of explains very nicely why both the research community and industry are so much interested in this adversarial attacks, and it's really great that we are getting ready just in case, it starts happening. So you've shown some really interesting, this would be kind of the first question from my side. So you've shown some really interesting potential actually for disturbing autonomous driving as a process. So where else do you see it, maybe in urban scenery?
Sorry,
in urban scenery, for example, do you see it, for example, happening? Well, this was a very obvious case, let's put it that way, changing, for example, traffic signalization, but do you see it because autonomous driving, they are relying on a very accurate maps, like what TomTom is doing with one of the labs we have at the UvA Atlas Lab. They're really relying on this highly accurate, maps, of the cities. So do you see this kind of adversarial attacks also happening with the other types of the objects, such as road infrastructure, bike paths? Imagine, like there are somebody tweaks a little bit with that, or you find it a little bit too difficult?
So I have found certain examples that really target autonomous cars, but I don't think that means that other cases are not possible. So I think generally there's no reason to assume that just because they target specifically road signs that this won't work with something else. And I think it's basically possible everywhere where it makes sense and where the decision maker is basically a neural network. Especially in object detection, it's also quite similar. For face detection, this problem arises since years. You can also look for an anti-face detection makeup, where some artists basically created their own adversarial attacks without really using it, using the technical part. But this doesn't mean that you cannot generalize this for any object detection methods.
Yes, excellent. It really made me thinking about some of these kind of applications now that we are more and more using in urban computing, that basically we should be ready to actually protect more and more parts of that pipeline, actually. And we have, in the meanwhile, a question from the audience. We have, it ended up by mistake in a chat, but I'm going to just kind of read it to you. Taco is Jan Taco is asking about potential for this kind of attacks in medical applications. Do you see that happening? I presume Jan Taco was thinking maybe about radiology or other type of medical applications relying on computer vision.
Yeah. Like, I think it's definitely possible, but for me it would be a question who would do that and with what extent. Like, I think to really modify the output, you would either have to have access to the medical machines, and then you could probably employ a virus where you then don't even need the neural network, because you can change the prediction afterwards anyways, or you would do it as the health institute to, for example, I don't know, for example, if you don't want to modify corona tests because you want to show that corona is not a real threat, as a lot of people do that claim that right now.
This is interesting, actually. I think what you are saying now, in one of my previous lives, I used to be a forensic scientist at the Netherlands Forensic Institute. And there we also discussed often how dangerous it can be if somebody has access to the physical access to the equipment, you know, like, and you can compromise it in a great many ways. But do you think that this, based on a question we got from Jan Taco, do you think, just out of blue thinking, you know, like if you go to a hospital, you know, like you go to LVG here in the East and you want to make your MRI scan, you know, security measures are not really kind of the same as in a case of military facilities, let me put it this way, you know. So do you think that at some point this could actually become a real threat, actually? Somebody, you know, people have different motivations, you know, like also you would wonder why people make computer viruses, malware and spyware, you know. But do you think that we may actually end up in a situation that somebody may be tweaking actually with the equipment itself, that's imaging equipment, or actually the analysis for whatsoever malicious purposes?
Yeah, like I can imagine that happens in certain countries. I think it's more likely than in others. Basically, everywhere where the hospital doesn't care about the patients itself, but rather about having nice statistics, like showing that they managed to treat a certain type of illness, or don't want to treat this certain type of illness, this might be effective.
I was more thinking about really hypothetical situation, you know, like somebody entering from a street hospital, you know, like, and you know, doing something to the equipment. But maybe this is too hypothetical. Anyway, I think really it's good that we are thinking about these things, you know, like, and I think your work really kind of does a great job in actually raising also awareness. It's a side actually product, you know, like, but I think it's really good that we are thinking about these things. Although it's not happening, I myself immediately start thinking of a few situations where, you know, maybe at some point we are going to be actually rethinking also different protocols, actually, even for medical institutions and so on.
Yeah.
So let me, I see indeed. So we have Jan Taco. I think he's happy about the answer and also agrees that we should be actually keeping an eye on this. Do you take into account worst case scenarios? This is another question coming from Jasper Kool.
I mean, I think that's now specific for the autonomous car. I think it is kind of a worst case scenario what I presented, because it, like right now, it would take a lot of effort. My father works in the automobile branch. I asked him how much effort would it be to really open up a car and deassemble everything until you find out where the neural network is and how to check it, such that you could then do this attack for any car of the same type. And he basically told me that's the same effort as building a new car. So right now it would be a lot of effort to really do this attack, and it's probably just that a government would, like, if they would really target a specific person, that they could do it, and in other cases rather not. But
so maybe related to this one, I think the last question actually for the time being, and then we can come back to any remaining questions actually after the second presentation. So this one is also interesting. Can this also have applications in finance? It's coming from anonymous attendee, but very interesting use case. Thanks a lot. Can this also have applications in finance, where I add noise to my data, time series, for example, yeah, in such a way that it looks natural, but completely throws off the predictions by machine learning algorithms? And attendee didn't say exactly what kind of application, but I can imagine something like maybe credit risk prediction, or maybe something when it comes to credit card fraud, or kind of other anomaly detection algorithms. Do you think this could be actually case there as well?
yes, I totally think. I also would go for another use case there. Like, I know that a lot of venture capitalists are using machine learning models to predict how good a startup will do in the future. So they want to buy the startups before they start doing good. And if you are a startup, you might use an adversarial attack to learn to do certain things to then get their models to give you a higher score, and then you sell your startup before because they think it will be successful, and then you just don't care about the startup anymore.
Very, very interesting. Actually, that's another one I didn't think. I was working a few times on applications related to credit risk assessment and these anomalies actually. But this is actually a really great example of another thing that could go wrong. I think this really made us all thinking about the future and actually what we have to pay attention to. And I would really like to thank you for a really great talk, and thank the audience for nice questions. So for the time being, I suggest that we move to the next speaker, and then we can come back to any remaining questions, after the second talk. So with this, I would like to introduce Inske Groenen, an excellent young PhD student from the University of Amsterdam. She's doing her research in multimedia analytics, and she's particularly focusing on urban computing applications, meaning analyzing our cities, analyzing the neighborhoods, combining different types of data, visual information with the open data, and she's trying to monitor and predict livability of the neighborhoods in a city. In a way, it's also related to the previous presentation. We've seen from Benedikt how adversarial attacks can be actually used to modify traffic infrastructure, for example. And Inske is going to be talking about object detection in urban scenery, and some of these objects are actually even related to road infrastructure. So it's kind of connecting nicely to the previous talk. And without further delay, I would like to give floor to Inske, and we are all looking forward to hearing what she has for us today.
Yes, thank you for introducing me, Stefan. Yeah, let me just share my presentation. It's here. Yes, so yes, as Stefan already mentioned, I'm going to talk about urban analytics, and specifically I'm going to introduce my work on panorams, and I've been working on identifying and localizing objects in urban context. And this is joint work with Stevan Rudinac and Marcel Worring. So yeah, I'm trying to analyze the urban environment, and cities are really complex, have a really complex and dynamic nature, and there are many challenges ranging from health to pollution to all kinds of challenges. And there's also really a large variety and volumes of data available. So there's a lot of opportunity to do very interesting things. But because of those characteristics, this really calls for an interdisciplinary approach to analyze this big data in urban spaces. And yeah, that's basically where urban computing comes in. And as Stevan already mentioned, I'm really interested in questions related to urban livability. So you can think of questions such as like, how come a certain area within the city is perceived as safe or unsafe? What are those factors that influence the function of an area that it fulfills within the city? And also, for instance, how does the design of a public space, how does that influence citizen well-being? So these are general questions that I'm really interested in, and I'm hoping to find some answers at least to some of these questions using urban computing or urban analytics. And there's been some previous work. So it was really interesting, this paper on city forensic, where they showed just based on visual inputs, so panoramas of the city, they were able to predict non-visual city attributes. And so they were, based on visual input, they were able to predict the crime within an area. And with that, they also discovered elements on, for instance, buildings that correlated either with high crime rates or low crime rates. And then more recent, and we step kind of more in the deep learning era. There, they also, in this paper, they also showed that based on visual inputs, they were able to predict whether an area was safe or lively, beautiful or wealth. So there is, based on visual inputs, we can train networks to predict these kind of well, what we call livability indicators or aspects related to livability. And this was purely on visual input. So I'm, with my project, basically taking it a step further and also incorporating different data sources and not only visual information. So like I already said, I'm really interested in finding out how the design of public space, so the objects and how those objects within the city, how they look, how does that influence urban livability? And like I said, cities are really complex. So in the first step, we really try to break it down. And with that, I started as a first step to classify and just detect those common objects. So you can think of buildings and trees. So these objects that are very commonly found in urban scenery. And then we came from an observation that think about Google Street View, but also, for instance, in the city of Amsterdam, the municipality themselves, they collect street level images, panoramic, and these. So there's really a large collection of panoramic street view images that are available to us online, but they are unlabeled, and we are generally very good in training networks when we have labels available. However, what we also observe is that there is actually a lot of information already available on urban objects. So cities generally, at least here in Europe, they are generally mapped out. So we have already in Amsterdam, for instance, a lot of information on where buildings are located, but not only buildings, but also, for instance, trees and trash cans. So this raises the question of, can we not use this information that we already have on those objects of where they are? Can we not use this as a supervision signal to classify and detect common objects within panoramas without requiring human annotators? Because as soon as we need human annotators, it's gonna be costly and it takes a lot of time. So can we not find an automatic approach? And now why would that be interesting? Like I said, so cities around the world are obligated to maintain precise information about the objects in public space. And these databases are, for a large extent, manually curated. And like I already said, that's expensive and very laborious. And it also frequently leads to errors. So maybe previously an object was mapped somewhere in the streets, but maybe now already the scenery has changed. And these databases are often not kept up to date as precise as we would like. So practically all cities have at least such databases, well, given errors, but there is already a lot of information on location of objects. And there is a lot of, there is this street level panoramic imagery available. So that really, for us, led to the question of, can we then deploy computer vision and multimedia analysis for this task? All right, so now I'd like to introduce my Panorams framework. And I will walk you through it. I will start with the annotation pipeline. So as you can see in the left bottom corner, we have basically 3 types of data. So we have this image data that is GPS located within the city. We also have geographic object information. And we have also, at least for Amsterdam, for which I have deployed this framework, we have elevation map data available. So for larger objects, we can even extract the height information based on that data. And using these 3 data sources, and I will show you a bit more in detail in the next slide, but we are able to extract those object features and 3D real-world measurements in relation to where the camera was of where the image was taken. And then we can map that using a simple camera model. We can map that to the image coordinates. And that results in an initial set of bounding boxes, and that we then refine using some geometric reasoning to basically refine those boxes and handle occlusion. And this results in a really large scale train set with automatically generated noisy labels, which you see in this image in the bottom. And that's really interesting, because this way we have an automatic pipeline which doesn't really acquire much human input to get really for really large set of images to get these labels. And as an evaluation, we've also come up with a crowdsourcing tool and protocol to then, from these noisy boxes, to get to really clean boxes. And that's basically on the top. And that's how we got our ground truth subset. So this is, we have done for really a small subset, just as a purely evaluation basis to compare how is the performance of training on these noisy boxes, and how does that compare to when we have really accurate labels. So yeah, here you see a little bit in more detail how this mapping or this generating of those bounding boxes, how it works. So we have a lot of features, and even for some categories, we even have a lot of detailed information, and also a lot of information that, based on the image alone, would be very hard to acquire. So for instance, on buildings, whether it's a monument or even the average number of rooms within a living unit or the surface area. And we have all this data basically on a map. And we have, like I said, elevation map data. Then we can extract relevant 3D measurements of the objects, and that, using a pinhole camera model, we map it to 2D coordinates. And then based, if some boxes overlap too much, so we can then handle occlusion, because we also have, for instance, the distance of the different bounding boxes to the camera. Well, this resulted in a really large scale train set with over 50 million noisy bounding box annotations, and for 24 different types of objects. Then I won't go into this in detail, but like I said, we also created a specific protocol for 360-degree images to get the clean annotations, the ground truth. Here's some statistics. So the noisy data sets is roughly 800,000 images big. So this is really at the scale that using human annotators, it would be very hard to generate a data set of this scale. Yeah, like I already said, 24 different types of objects, 50 million bounding boxes labeled object instances. And then we came to a set of roughly 5,000 images, ground truth annotated, but this also amounts to about 8,000 labeled object instances. Then some more in detail. One of the challenges of this dataset, the Panoram's dataset, is that there's a very large class imbalance. So there are some classes that are very frequent, such as buildings and trees. And then there are some objects that you hardly see. So ferries, traffic lights, for instance, reclamezeil. So that makes it very hard that's really one challenge to train this data set of how you're going to get good performance on all classes. Basically, that's what you want, even though some you have very few examples of those. And to make it matters even worse, if you actually look, because this was on how many of classes within an image, and if you look at the total number of object instances, then you see that the dataset is even more skewed, because there are multiple objects within a screen, within an image, and then if you look at the absolute object instances, then you see that this skew is even larger. And then another challenge is that because we're looking at street imagery, there's not a very clear center of focus, and also and there are multiple objects within the scene, plus their size, the size of the objects in relation to the entire image size is quite small. So all these points or characteristics of the data set make this actually a very hard data set to train on, in the detection at least. That's all right. So I will show just some numbers just to show you a little bit, to give you some insights on how well this trains. So here I've only included those classes of where we actually see a performance, at least at this point. And so what you're looking at is in the top, basically trained on the noisy entire sets. And in the bottom is the ground truth set. And we've also included here as an evaluation, if you also use the noisy boxes evaluation of whether they show some trend, basically. And what you should take away from this is basically what you see is that those objects of which you have a large collection of examples of in the ground truth, at least, they train very well. And there's still a very big challenge of training on these noisy boxes, because you really see that the performance drops dramatically. So some conclusions. Yeah, so by using really this diversity of multimedia sources that are available to us in the urban context, it is possible to map a great variety of classes onto street level images. And this way we can, a large scale multi-label urban data set can be created solely from open data and without requiring human annotators. And like I already introduced a little bit, is that we also introduced a really challenging new task. So how to train object detectors with those noisy bounding box annotations. And that's really very much still an open question. And then just to give you a little bit of where do I go from here? Where do we go from here? So the next step is really will be to investigate how those common objects together shape urban objects. And then we like to take it even one step. And then we introduce also area statistics and citizens feedback in order to do that. And then we really want to take it one step further. So then we look take into the challenges and and then we will investigate how the design of an urban area related to those objects that we've now so far been looking at. How does that affect livability? And again, we take area statistics and citizen feedback into the loop as an extra data source. All right, that's it. Questions?
Thank you, Inske, very much for a really nice presentation. It's good to see that our multimedia and computer vision techniques are already gaining a maturity level, that they can be actually deployed in analyzing our urban living environment and actually trying to estimate livability and help the cities actually monitor, for example, state of assets, as you showed nicely in your presentation. And we have some questions coming from the audience. Jette Schoormans is commending you on your work. Very interesting work, Inske. Is or will the panoram's data and method be open sourced?
Yes, so yeah, we're almost close to releasing this data set open source, so there will be a website, because we also very much, we're basically setting benchmark on this data set now, but we very much want to invite the whole community basically to work on this task and to work with this data set. And the methods, yes, so the method will be described in detail in the paper, and we will at least also make this crowdsourcing tool, and also that part will also be made public on open source.
I wanted also to mention that the city of Amsterdam already actually agreed to release the data. Maybe you can also say something about panoramas. Panoramas are actually openly available, but also the annotations are going to be, yes.
Yeah. So the panoramas are already open source because they are provided by the municipality of Amsterdam. But yeah, the labeling itself, not yet, because we're in the process of basically rounding it all up and making sure that it can be made public open source. Yeah.
Yes. Also, big thanks to the city of Amsterdam actually to contributing to these open source initiatives and open data naturally. So another question was from Jasper Kool. What kind of issues you think about to tackle in the city?
So what we're looking at now, so at least in Amsterdam, they have I think they have multiple indicators basically. So they really have a wide scale of indicators, so per area. So these are usually acquired from surveys from the citizens themselves, and that has resulted in some score or different scores on different aspects of livability. So off the top of my head, there's even on how pretty they think the neighborhood is, or on cleanliness, for instance, and safety. So we will be taking those indicators and trying to incorporate that. So it's a large scale of different aspects of livability, basically.
Thank you, Inske. There is another question coming from Pranav. How do you get the bounding boxes for images? Is it using an off-the-shelf pre-trained neural network?
So the noise. So we actually generate, or we've acquired those bounding boxes ourselves. So the noisy boxes we really generate in an automatic way, based on those three types of data that we have. So images, objects, data, basically on a map view, and this elevation map data. So we really had this pipeline to generate those noisy bounding boxes in an automatic way ourselves. And then those clean boxes have been acquired via crowdsourcing, via Amazon Mechanical Turk. And we did a really large scale crowdsourcing task there to acquire those clean bounding boxes.
Excellent. I hope this answers the question. Oh yes, we have another one coming in a Q&A just now from Jasper Cole. Do you share the outcome with HTTPS open source player.nl open source platform initiative from the government?
I didn't know about this platform, so it's new to me. But it sounds interesting to actually check it, yeah, and to maybe contact them to also share it there. Thanks.
Excellent. Maybe we have another 2 minutes before the last part, actually, because our colleague would like to make a small announcement in the last 2 minutes. So maybe the closing actually question for Inske. Do you see actually these kind of models translating easily to different cities? Because most of this is done in Amsterdam, and Amsterdam is a very specific, I would say, architecture-wise. So considering that your project is done with 9 different cities in the North Sea region, so do you see a kind of transferability to those cities as well?
Yes and no. So I think for certain objects, definitely. So I mean, there are key characteristics that from city to city, you can still, I think, train on. I mean, this of course has to be, we need to experiment a bit further, but yeah, I think definitely for certain objects it can be done. I think if certain objects really become kind of very typical for the city, so the more typical the appearance is for the city, I think the harder it is to transfer it to a different context. So I think here and there are definitely challenges, and it's not going to be something that's just take it and it's automatically going to work for the city. So I think you need to tweak and make some adjustments here and there. But I think it's definitely a good starting point. Yeah.
Excellent. Thanks a lot. And I was asked to finish exactly at 12:58, which is now, because we have a small announcement coming from Vladimir Nedovic. So please go ahead.
Yes, thank you. Good afternoon, everybody. My name is Vladimir Nedovic. I have a master's and PhD in AI from University of Amsterdam, actually in computer vision. This is where I know Stevan from, among others. But I'm here on behalf of AI Startup Lab, which is here in Science Park. And it is part of ACE, Amsterdam Center for Entrepreneurship, which is the incubator, startup incubator for Amsterdam's knowledge institutes, universities, and medical centers. If you have a dream of taking of building an AI-based startup, or you're toying with an idea of starting something on your own, if you want to take any of your ideas or initiatives further, please talk to us. We want to offer any students, whether technical or business oriented, a platform to work on real world use cases, to communicate and collaborate with corporate partners, to experience the most relevant aspects of entrepreneurship in a sort of a pressure cooker way. If you're interested, the email address and the link is clickable. Please talk to us. Thank you very much.
Right. Thank you very much for that, Vladimir. This webinar is now coming to an end, I'd like to give a special thank you to SABA, the Study Association, for partnering with us on this webinar event. I'd like to give a really big thank you to Stevan for moderating this webinar so excellently.
Thank you.
And of course, a
big
thank you to Inske and Benedikt for your really informative presentations. Thank you very much. Yeah, that's it from us today. Bye-bye, everyone.